involved in mineralization for about 12 years now. I know Eddie the same time, and I happen to know Olaf Scheuling for about I think 30 years or maybe 35 years now. And so therefore I'm involved in the mineralization for quite some time now. And I met Sven, I think 1.5 years ago or 2 years ago about that time, where we came in contact. So that's why I'm here, I think. My talk will be, let's say, about general introduction, about olivine, and later on we'll talk about 2 more or less business cases about that, and then I will leave the floor to Eric. I will give you one chemical formula. My background is physics. As most people are aware, if you burn coal, you get energy, you get heat. But what most people don't know, if you can get even more heat or get into a more stable form by forming carbonates. At this moment, there's a parallel session in the States about air miners, and Klaus Lechner is speaking there. And he says, eventually we have to get this CO2, gaseous CO2, into salt carbonates. So that's the most stable form. I give you only one formula. There are more formulas, but I think we're not chemical engineers here. But let's say it shows you how the reaction is, that it is exothermically. That means that the end product is stable, so it won't come back. Let's summarize that way. Let's summarize that. And of course, then mineral carbonate. This is a very new field. The very first publication was in 1990, which is, I think, quite remarkable, because CO2 capturing is already been done since the First World War in the submarines. So, but you see, it's a very new field, and therefore it is quite fast developing. But yeah, the very first idea about using silicates, using olivine to sequester CO2. This is a picture about the global CO2 balance. The expert might notice there's a rather old balance because currently the levels are much higher. Which is interesting is, from a physics point of view, it is more or less in balance. There is only a off term which every year gets the level a bit higher and higher and higher. These are the industrial emissions and the land use change. And there happen to be volcanoes emitting CO2 that used to be sequestered by weathering. So this weathering process is very naturally, it is happening for millions of years, and it was nature's thermostat to keep the CO2 level and the temperature reasonable in balance. As this process was running on a modest scale but for a very long time, it meant that most of the carbon is currently stored in a very stable form, limestone or dolomite. The next time you go to England, don't fly. You take the boat or the train and look at Dover. Think that's all stored CO2. So by far the biggest amount is very safely stored. And what you can do is divide this CO2 into 2 subsystems. One of them is dead, is not taking part of the biosphere, and the other one is taking biosphere. And then you see that the amounts are getting completely insane, I would say. That you see that the problem we are having with atmospheric CO2, I wouldn't say it's neglectable, but from a scale, of course, it is small. So, and what we're currently doing is pumping lots of recoverable fuel from this dead reservoir into the atmosphere, which is having all kinds of consequences. So we need, let's say, we need to push it back from the live atmosphere into carbonate again. There are a few ways for doing that. It is happening by nature, as this is already proceeding for millions of years. You can do it in a chemical system. I will briefly touch that. You can do it on land. I'll briefly touch that, and then you can do it at sea, beaches, and Eric will explain about that much better than I can do. The natural CO2 uptake is quite big. I found a number, roughly 1 billion tons of CO2 is every year already sequestered by this natural process. As we emit about 40 billion tons, you see it is about 2-3%. So not sufficiently, but on the other side, 1 gigaton of CO2 is a huge amount. So you see nature is already partially healing it. But of course, as we're emitting so much CO2, it's only very partially indeed. That's, yeah. What you can also do is, this was already subscribed in IPCC about, I think, 15 years ago. Then was the idea, if you have CO2, put it into a chemical reactor, add the minerals to that, let them react, form the solid carbonates again here, and then put them back on the mine. I think that the idea didn't evolve the last 10 years for a few reasons, but let's say partially processed, the reaction is not very fast. And partially, of course, there is no business case, because if you need to mine it and then put it back at the mine, yeah, your business case is only depending on the CO2 price. That means the whole cost of mining, processing, putting it back needs to be paid by the CO2 price, which will happen eventually, but not for the very first market. So therefore, we shouldn't put it back on the mine, but we should make it into products and then sell the products. That means you can get CO2 as a resource, and then you still need CO2. You still sequester it, but then you see you get a different focus. You're making products with that. I'm doing that with the company Green Minerals. We are developing a process with a high pressure chemical reactor, and then we make a few products. I got the first demo types here. In paper is quite some lime used. We can replace the lime. In polymers and plastic is quite some lime used. And we made the very first concrete type of things with that. So then you see you still need CO2, but then your business case is more depending on the products you're making instead of on the CO2 you're disposing. This is still in the research phase. We can sequester about 500 grams per batch. So it won't save the world for this moment, but at least let's say we're doing that. Another way of handling that is, let's say, taking nature, do its thing. We made a model to calculate how fast reaction is. And now you see at the bottom, the time scale is years, which frightens off chemists and physical people, because they would like to have a time scale of hours or minutes. On the other side, if you're looking for applications which are in the same range, then it's not that bad. So let's say if you're looking for a civil application, typically a civil road or a railway track will last for 30 years. So that's not bad. If you're putting it on the beach, it might react faster, but even if it would react, let's say in 10 or 20 years, it still isn't that bad, because you're talking about years. To put some more physics in that, on land it goes a bit faster because the rain is more acidic and the ocean water is more alkaline, so it will go a bit slower. But then these are, let's say, models. We have to validate the models. If you put it on the beach, what will happen most likely will be that the constant erosion will get a much faster reaction than you would expect. So, but let's say this is at least a first base model to see what the expected reaction rate will be. I'm helping Eddie Wenker. Most of you know him for the last 10 years. And he is selling green sand, olivine for a range of applications. And as you can see, they're all used to replace existing civil products. That means you avoid getting into a geoengineering discussion, because you would have made this pad anyway. And then the question is, don't use the standard basaltic or granite material, but use this kind of material. You would have made this railway track anyway. You would have put anyway some pebbles here to avoid the weed and the grass from growing here. So therefore, and of course you can see this railway track will be here for the next 30 years. So if the reaction is 30 years, it isn't too bad for that. So Eddie is scaling up slowly. He's getting more and more projects. And one of the more recent things he's doing is selling CO2 credits. With this credits, he can buy olivine, and with this olivine, he can give it for free or for a very big discount to more social projects. That will make it easier, because at this moment, let's say people would like to use in their own garden, but if their own garden is too small or not suitable, still you have some CO2 compensation. So that's now starting to evolve. We are working more on that, but at least, let's say, this gives you another perspective, and also, let's say, it gives you new projects, because typically, if you talk about projects, people are thinking that it's too expensive. And of course, as you're starting, it is already more expensive than conventional pebbles. So therefore, you can get the price difference over by that. Currently, the state is they're scaling up the sales. Scaling up sales means lowering prices, just more logistics, bigger ships, getting more projects. He's selling more CO2 credits, so we're getting more demonstration projects, more PR, and we're working on getting more science that we can better calculate in each circumstances how fast the reaction rate is. So you see there are different ways on using this olivine. And one other way is for Eric about Project Vesta, putting at the beach, which has got its own merits. So now I have to stop sharing. So.
Okay, thank you, Paul. Before Eric starts, anyone who would like to pose a question?
Yeah, I have a question. Oh, I'm not sure. Can I? Yeah.
Yeah.
Well, on this carbon credits idea, which I think is really interesting, can you maybe elaborate a bit on how that works? Who's selling the credits and who's buying them specifically?
Yeah.
The authorities involved. How does that work?
There are no authorities involved at this moment. They're very, very, very voluntary. They have been sold. People are buying them. Let's say is a whole range of people. One of the one you saw in the picture is a professor from the University of Twente, and he used to fly before the corona. And of course, that's his work, his conferences. So he said, "I'd fly as less as possible." And so he calculated how much the flying was. He got his model for that. And with that money, there was a parking space realized at an environmental park. And that's been traced at the website of Greensand. If you buy CO2 credits, you get a certificate with a number on it. The number you can fill in on the Greensand website, and then you see which projects is being realized with that. So that's already happening. What we are working, let's say, is better making the accountancy stronger indeed, yes. So, but let's say at this moment it's very voluntary. There's no government involved.
Yeah, so it's a certificate that's produced by Greensand itself. Yeah. Okay. Okay.
Yeah.
Okay.
But of course, let's say very transparent that you can see where your project is realized. That's
yeah. Cool. Yeah.
And we'll have some discussion on that as well in after my presentation. So happy to jump in. If there's are there any other questions? All right, let me get my screen share in here.
I have one question.
Oh, go ahead.
Sorry, I put up my finger, but maybe I should just be screaming. Can you go back to a figure? Is that or does that take too much time? You showed this figure where you were talking about the well, it went a bit quick, but you were talking about the amount of CO2 that was taken up by land and by the water. I was trying to explain to understand that figure. Can you explain in a little bit more detail what's going on there?
You see the here I can.
Yeah.
Okay, sorry. What is happening here? If you put olivine, sandy olivine, with a particle size between 0 and 3 millimeters, these particles get slowly washed away.
Yeah.
And the speed, let's say, is depending if it is more acidic, it goes faster. If it is less acidic, it goes slower.
But with washed away, you don't mean it's on a beach. You mean it's used up.
Dissolved.
Dissolved.
Just
Yeah.
like
Okay.
put the sugar in your tea. If the tea
Yeah.
is
Exactly.
cold, it goes faster, and if it is cold, it goes slower. Indeed, yes. And so let's say the temperature is a pH, determine the reaction rate. And then you can say, okay, if I wait half a year or 1 year, so that's, let's say, well, we do the calculations. We validate the model for a few cases, but there are, being honestly, a few uncertainties about that. If you put it on the beach, like you see on the background of Eric, you see the constant erosion of the waves, which will most likely get more erosion, like a free grinding machine, which will probably imply that the water rate will be much higher than you expected because there's more erosion taking place.
So because this figure, if you add up the two of them, I guess that's the total amount of percentage that is dissolved, right?
If you put it, let's say, I put here 30 years. If you put it in water without any agitation, after let's say 30 years, 10% will be dissolved. If you put, let's say, 100 kilograms of olivine in this alkaline seawater without any wave action, then after 30 years, 10 kilogram would be dissolved and be flushed to the ocean. If you put the same 100 kilograms in rainwater, you would 25 kilograms dissolved by the rainwater.
Okay, and so why is it flattening? Why doesn't it completely dissolve?
It will, because let's say the particle size, if you use very small particles, they will be like this. If you use very coarse particles, they will be like this, because let's say there is a certain amount of finer particles and coarser particles.
Okay, I'll save other questions for later. Thanks.
Let me give. Yeah. Yeah.
Are you going to continue, Eric?
Yeah, okay, I just want to make sure. All right, I'm ready to go here. Give me 1 second. And we'll pull that out. Share screen. And
At the back, you can see the agitation there already.
yeah, so yeah, we're already agitating over there. So let's get the share. Okay, great. Can you all see my screen? Can you all see?
Yeah.
Okay. Great. So, all right. So Project Vesta, we're turning tide on climate change. And essentially, as you know, as Paul noted, you can do land weathering or ocean weathering. And this background on the beach here and in my video screen is a real green sand beach, as we touched on. So we're actually just mimicking nature in a way that's directed to get the most CO2 removed. So I just want to set a framing here for anybody. Obviously, you guys are all in climate cleanup and you're totally aware of the situation that we're in, but realistically, there's no debate that we need to figure out negative emissions technologies or carbon dioxide removal processes, because the Paris Agreement relies on them extensively to meet the limits, especially in every single overshoot model that keeps us at 1.5 degrees Celsius. So there's essentially no way we're cutting in time, which you could see with this pandemic, that even everyone's staying home and has done the most aggressive lifestyle changes, and we only have a 10% reduction, but we really need to be on track for a 15% or more reduction. And this great report by the European Academy's Science Advisory Council essentially says, if we don't figure out these technologies now, because they're going to take some time to implement and research, then we're going to condemn humanity to a dangerously warming world. And so that's the kind of perspective that we come from when we're trying to put together our project. And so Paul also mentioned the carbon cycle and the long-term way that Earth removes CO2. The problem, however, is that it's too slow on its own, and you have to wait for chance tectonic forces. So the calculation that 1 gigaton is being removed right now, essentially a majority of that is in Southeast Asia. About 45% of that weathering is in a single region. And this has happened in Earth's history where usually when rocks are near the equator weathering, it has a outsized effect on CO2 removal. There's sometimes when it, like not the latest one is basically when the Himalaya plateau, the Himalaya mountains hit the Tibet plateau, and it caused so much ultramafic rock like olivine to be exposed that it caused the global cooling that we're coming out of. And essentially, we're just trying to direct that in a way that eliminates the need for time and chance appearance of the rock in the equator and the humid tropics. And so we take the fastest weathering rock, which is olivine, and we use that in a way that it will grind down more quickly, which I'll discuss in a minute, to remove CO2. And like, it's pretty simple. We quarry olivine from nearby locations, take it to the beach, and then use waves to capture it. Real briefly, our chemical reaction is a little bit different. Well, just zeroing in on exactly what's going on is basically CO2 is dissolving into the ocean constantly. And when water and CO2 mix, you get carbonic acid. There's ions in that water that when the olivine enters the water, the ocean, it causes those ions to bind with the materials from the olivine. And that leads to the formation of bicarbonate, which is an alkaline molecule. So it actually deacidifies the ocean at the same time. That bicarbonate will become carbonate, and then eventually calcifying organisms will combine it with calcium to make calcium carbonate, which is essentially coral skeletons and shells of all of the animals. When they die, that goes into limestone, and that's what they're talking about as the end state of carbon. The lowest is rock. And so 99.9% of rock is in carbon. And so it makes sense to take this 0.00000, like less than 1%, and put it back into rock. And so as Paul also pointed out, this is like a 30-year-old idea with Seyfried's looking at this and going forward with Lackner and others, and essentially bringing together a couple different concepts to make this a reality. And so what we're doing here is trying to help advance this process that was created by the theoretical concept by Scheiling and a number of other Dutch scientists and other global scientists. So and I'm a futurist. I'm actually don't have a purely scientific background, but in futurism and in advancing technologies, one thing we look at is something called a technological readiness scale. This is originally developed by the US military and has been used to develop the most advanced technologies in the world. And now the European Union has adopted it as well. And it essentially is a way to evaluate a technology and determine what level on the scale is it at. And usually the basic technology and individual pieces are done by governments and universities. And then when technology is ready to be deployed, when there's a business model, when there's a way to make money off of money going in, the private sector steps up. However, there's something known as a valley of death, or the chasm in business model development, which is a huge problem. And so Project Vesta was formed by myself and a number of others eventually to help bridge this gap, to take enhanced weathering in the coastal environment from the valley of death to the beach. And we have a number of puns like that from going from the lab to the beach. And I'm going to go over some of the steps that have been taken thus far and what we're doing going forward to move this out so it can be available as what we believe will be the world's premier carbon dioxide removal technology. And the reason we believe it will be that premier technology is because olivine is highly abundant. Each of those red dots represents something called an ophiolite. And an ophiolite is a place where the seafloor has risen to the surface through tectonic forces. In that layer, without getting too many geology terms for you, there's a layer of 90% pure olivine called dunite. And those are all, it's an entire layer of that is found in each one of those red dots. Some of them are accessible, some of them are already being mined. Many of them can be brought online fairly easily. And if we take that rock, volume of about 7 kilometers cubed in 2% of the world's shelf seas, So each of those green on the Ample Beaches area, I'm not sure if you can see my mouse, but each of these green areas is a shelf C. And the red represents the equator where it's warm enough to weather rapidly. So it's possible to get 100% of anthropogenic emissions removed using this process. And essentially, the price of rock is around $4 or $5 a ton. You add in a little bit of transport and other things, and essentially we can get to a price per ton of CO2 removed to be less than $10 per ton. And it requires no new technology, just essentially directing our existing mining technology and finance towards that. And so previous weathering mech schemes, whether in the ocean called open ocean alkalization and much of the land weathering, have some issues in terms of the weathering rate because of a couple of factors, but one of them being the energy used to grind the rock down to sizes that are small enough to weather rapidly, and the other one being transport distances. So if you can optimize your process to minimize the energy in grinding and the transport distances, life cycle assessments say that this process can be as great as 95% efficient, meaning we only lose 5% of the net sequestered emissions from those processes. So essentially it's 20 times more effective than at removing CO2 than the CO2 generated in the process. And so generally the biggest problem with the weathering rate is a silica coating that builds up. And so this this yellow color here represents a silica coating that rapidly builds up on the outside of olivine when it weathers. Because remember, it's made of magnesium and silica. And these yellow dotted lines represent what happens when it's agitated through mechanical activation, and that is the abrasive forces cause that silica to be removed rapidly. And so we're actually going to look at this model here, which is similar to Paul's model. And this model was actually created this model was ran with some assumptions by some Dutch researchers who actually were trying to disprove that this process could work. They were funded by Shell, and they were publicly feuding with Schuyling due to his aggression of wanting olivine weathering to be the only process used. We at Project Vesta believe, this is a bucket of solutions, and that ours is one of a number that will be utilized, including tree planting, direct air capture, land weathering, etc. However, we do believe that if we need to remove 20 gigatons a year, our process can do at least 10 gigatons a year. So we're happy to work in tandem with other processes, but we're also prepared to stand for be ready to go to remove all necessary negative emissions. So let's take a look. They say that 3 millimeter grains will take over 100 years to weather just 10%. But let's be mindful of the black line and the yellow line, which show 10 micrometer and 30 micron particle sizes that they can weather up to 90% in 5 and 10 years, less than 10 years. So let's look at a quick experiment that was done and that proves this wrong. So on the top right, you see where it says coarse fraction. That represents sand that's 2.3 millimeters. So based on that weathering rate from the previous slide, this should take somewhere between 30 and 100 years to weather 10%. But just 2 months on the shaker generates fine fraction that's essentially down to the micrometer level. So it just shows that putting the rock in motion, the collisions cause fine fraction to generate rapidly. There's without getting technical in the structure, it's very hard to model olivine because it's tetrahedral structures of silicon, and when water gets in, it breaks down the crystal rapidly. So if you're removing the silica coating and you're having forces that further cause collisions to break the weakened crystal down, it can weather at rates that no model thus far is able to calculate, including that model which was developed by Paul and is the best thing we have right now. It was developed along with Jos Vink at Deltaris, which is a great Dutch group that we're partnered with. But realistically, there is no model right now that represents real world weathering rates with collisions and motion. And so you could see here another quick demonstration that motion is highly implicated in accelerating the weathering rate. And so what we're looking at is a chart of the pH level over time and with and without motion. So if you look at this gap between 0 and 5 days, that's a weekend when they shut down the flume that you see. And so essentially the pH went from 8.35 down to 8.13 or 2 over the weekend. And when they, as soon as they, what happens is that silica coating's built up almost immediately. And so as soon as they start moving it again, you see the pH rises, which means the reaction is ongoing. And the reason the pH is rising when it stopped is because just like the ocean, CO2 is constantly entering in the top. So if you put this into motion, the weathering reaction continues onward. And you can look at when they refresh the water, it starts all the way down by 8. And as soon as the motion is increased or started again, the pH rises. And so again, motion plus collisions equal, and the abrasion of the surface equals rapid weathering. And so nobody has yet proved this in nature. And so these lab experiments are on this technological readiness level around this 1, 2, 3, and 4. But we need to take this, and we proposed a poster, which Paul was a remote co-author on, and we brought in some other scientists. We presented at the American Geophysical Union, which is the largest geological sciences meeting of 50,000 people in San Francisco last year in December. And we had, it was called From the Lab to, Olivine Weathering from the Lab to the Beach, and it laid out what we were going to do. And that got us into the front, the newspaper locally here. And then since then, we actually found a pair of beaches, and now we are not just theoretically going from the lab to the beach, we are there. I've been to this beach, I went and monitored it and drew samples. That's not me, that's a PhD scientist we hired to go along with me. And essentially what we're doing here is bringing this technology from the lab to the beach. And this is the beach where we're going to be recreating the natural beach in Hawaii. We picked a similar bay. And this is not about the speed. This is about the safety and the precipitants and making sure that we can do this safely. And I'm happy to take many questions on this afterwards. But essentially, we've picked before and after. We have like the most robust science possible, the design here for this experiment, which is BACI, which before and after control, where we're going to monitor the bay. Right now, we have sensors, and we're taking monthly and weekly measurements to measure dissolved silica, alkalinity, a number of things, and determining the signal there before we go. So we have a before and after. But to further make our data even more robust, we chose a pair of bays. So we actually have another bay right nearby, which we're also monitoring, and which has very similar characteristics to the experimental beach. And that will remain as a control. So there will be not only before and after, but there will be in parallel comparisons to the other beach. So once we lay down our olivine within 6 to 12 months, once we have a signal determined that we're confident is normal through the seasons, et cetera, we will then deploy olivine in that green outlined area. And so we will be basically moving from this beach to the experiment. And so right now we have raised some funds, but we need more to carry out the beaches, monitor them for 2 years, and deploy additional experiments. So that's kind of what's going on right now. In the future, once these beaches are done, we have plans to go with demonstration projects around the world, showing that it works. We already have inbound interest from countries looking at how they can implement this to meet their Paris Agreement goals, and in general, show that they're doing stuff for negative emissions technologies. And so that we believe that single countries can use this to passively meet their carbon emission targets. And essentially, countries are already spending millions and millions and millions of dollars nourishing their beaches with sand from erosion. So why not have sand that's going to erode, but also suck up CO2? And then there's collaborative ways, such as the southern bight of the North Sea, where the entire Europe, Britain, France, Belgium, Netherlands, and even Germany, if they want to get in, Norway can supply it, they have the world's largest active mine. that is the equivalent of 5% of the world's CO2 emissions could be captured there, and those countries contribute less than 4% of the emissions. So the idea is there's mechanisms for global scale upscaling of this. But what's needed and what's crucial with what Project Vesta is going to create is a model that takes the safety data from the release of precipitants of olivine weathering, which can, for example, some people will say, what about nickel? What about this and that? There are models that have been created also by Joss Fink and Paul that we're going to integrate with a weathering rate model with a life cycle assessment so that you could take this model, bring it to any beach, put in the wave energy, put in the temperature, put in the source of the olivine and the chemical analysis of it, and it will tell you the safest amount you can weather, and it will pump out the net tons per CO2 weathered per year. So essentially, this gives you a model that you can use to sell credits, et cetera. So Project Vesta is basically going to sit at the middle between the public, the governments and countries and scientists, and coordinate all these different aspects of how to make this model, how to fund it, what experiments need to be done, get those experiments done, get the permission from the governments. It's a lot of work, and that's why it hasn't been done thus far. But we are going to sit in the center. We're a nonprofit to facilitate all of this stuff until there are green beaches all over the world. And so that's kind of our mission, is to do that. I don't know what's on that slide that's loading, but we put together a team. That's other scientists that are our science team. I don't know why it's not loading. There's me, there's a number of people that we have on our team in addition to 3 or 4 scientists, including Frances Montserrat. I don't know what's going on with the previous slide. Let me see if I can get it working. But basically, we're partnering, we're looking for more partners, we're looking for as many scientists to bring under our umbrella as possible. And the idea is, with all these people together, we can build this model. We can work with communities we're selling jewelry, for example, and working on the public awareness side so that we have influencers and people and celebrities that are representing the project and getting the conversation going for carbon dioxide removal. So we're not just a solution, we are like the tip of the spear to bring forward all carbon dioxide removal projects. Because the idea is if people are we're creating a demand in the populace for these projects, then when that's what's called the social license for carbon removal. To do any sort of project, you need this YIMBY, which means yes in my backyard. In San Francisco, we have a lot of NIMBYs, which is not in my backyard. People who don't want housing, who don't want these other projects because they may mess with the current model. And so we are trying to create a groundswell of support in the people, in the science, and in the government. And so we're working the science of the government. We're working to make sure that enhanced coastal weathering is featured strongly in the IPCC's next report coming out in 2022. We are working then there's going to be a stock take in 2023 where countries have to look, since it's been 5 years from the implementation of the Paris Agreement, what have they done? And we want to have this technology in 2023 on a silver platter to say, well, you failed and it's obvious, but here's a solution that you can use to meet your goals for the next 5 years. And that is kind of what we're looking at doing. And just to summarize here, looking at the other technologies, trees are great, but they can burn in one day. We look at that, Australia, the Amazon, California. It's really not something we want to rely on. I think we should put as many trees that are down. Trees are beautiful. They make cities less hot. There's so many great things you can do with trees and soil and regenerative agriculture. We're totally supportive of those. But we need something that we can rely on that's permanent, inexpensive, doesn't compete for resources. Because if you're afforesting, that means you can't grow food there. And so those are issues. You need water. You need to harden those trees against, climate change. In 40 years, are those trees going to grow there? Or are they going to die and release the carbon? BECCS can cause more climate change, which is bioenergy carbon and capture. You grow trees and then burn them. It's ridiculous. And that's what the Paris Agreement relies on. Direct air capture is great, but you might need the total world's energy just to power the fans to remove enough CO2, and then you still have to store it, or it goes into fuel and can be re-released. Direct air capture might be great to make fuel for jets that doesn't have all these other terrible things in it, but will it be able to scale to 20 billion tons a year? No, not at all, no chance. And similar, biochar has some of those other issues. And so we're left with not many other options except coastal enhanced weathering or other weathering or sequestration with the trillion tons of rock available to do this. And that is how Project Vesta was formed, is I analyzed in a think tank all of the methods and then saw coastal enhanced weathering, yet didn't see any projects doing it. And so we set out to make that a reality. And that is what we're doing. It has all these other benefits like deacidifying the ocean, yada, yada, yada. And so we are moving this forward. We're hitting these milestones. We've already raised significant funding. We have significant business model validation announcements coming soon. And we're essentially raising $1.5 million to do all these experiments and run the organization. The idea is within 3 years, we'll demonstrate this, essentially the safety and viability, and then we're going to work to optimize the speed with a number of pilot projects, probably on the order of 1 to 5 to 10, with different locations that prove and validate our model, and then we'll synthesize all that together with the research and deliver this to policymakers and the world for implementation. So yeah, that's Project Vesta in a nutshell. And, we have some frequently asked questions, which I will open up to. I won't ruin the questions if you guys have them. And yeah.
Oh, that's fantastic, Eric.